Yeah, I think we can start with this session, today's session. So, again, to all, like to those people who have just joined, so good evening. My name is Shubhanshu, as you can see in the slide also. So, I will be taking your live sessions for this course, and yeah, so I think most of you will be UG students, undergraduate students. Uh, okay, it was let me admit others. Admit. Yeah. So yeah. So I think before starting with this course, if I can know about my audience, if like if you can unmute or you can like even say in chat if you are undergraduate or if you are a working professional, and yeah, you like whatever you want to say. So just quick thing, we'll do this before starting the course. So anyone can start, whoever wants to volunteer. So anyone so you are from, are you doing BTech, MTech, or like PhD, or you are working somewhere?
I am doing BTech.
Okay, nice. So you are in second year, third year?
Second year.
Okay. And what about others? Doing PhD, okay, nice.
Good evening, sir.
Good evening. Good
Good
evening.
evening, sir. This is Dr. P. Shashavali. I'm
Okay.
working as a teaching faculty
Okay,
in
nice.
SK University,
Okay.
Anantapur.
Okay.
Some of our students are going to register in MOOCs course in this course, electrical measurements and electronic instrumentation.
Okay.
So I will be in our curriculum. We have a mentee and mentors concept. So I am also going to register this particular course.
Okay. Nice. Yeah, okay.
Okay, thank you.
Great. So okay. So we have a whole spectrum of people here, from BTech to like even faculties also. So it's very good. Like it's very nice to see that. So we'll start with this introduction. The course name is Electrical Measurement and Electronic Instruments. I think you have been through the first week lectures, and regarding myself, I am a PhD student in IIT Madras, and this will be my second course which I will be taking live sessions for. So if I do commit some mistakes, so please let me know. um, yeah, so I will learn from you, you can learn from me, so it will be two-way interaction, and yeah, we will proceed like this. So if I start with this, how we will be arranging this live session. Uh, so we will have, we can do quick revision of what we did in first week, and then after that we can have some questions, we can say practice questions, so which can help you in helping you go through these assignments and all. And then we can have also doubt clearing doubt, if you have any doubts or something, you can ask me in the end also, you can ask me in the between also, whenever you want to. So yeah, so I think most of things will be like this. So if I find like there are so many uh, people here in this live session, then I can start straight away with questions, practice questions. So I will not go with revision, but if you want to ask something related to that lectures, so then you can interrupt me in between and you can ask me. And otherwise we will be solving lots of practice questions, and so that you can have an idea. Okay, so this is basically, since we are dealing with measurements and electronic instruments, so if we will not see more questions, then it will not be good. So just to have just to know you about, okay, like this is how these electric instruments work and their behavior and all those things. So that's why we'll be solving lots of questions. And yeah, so the things will be like this. And any other suggestions if somebody wants to say, or you if you want to add in this thing, Any other suggestions? Like, so can or we can add like something like that. If not, like first of all, so we'll start with this. So right now, if just I will skip this revision part for now, because we have like I think quite amount of questions today. So we will first go through that, and then I think your assignment due date is 9th of August for first week assignment. So maybe it can help you in solving those questions also. So for those who have not solved the assignment questions. And one more thing, like there was some issues in that discussion forum. Like if you're trying to ask some questions, so just collect your doubts and create a thread in that. So like don't try to like it is not good. Like you are asking each and like every time you are asking for different in a different mail. So just in your name you can create a thread, something like that. So it can be trails of questions in that, so it will be easier for us to answer also in that case. So okay, so first of all, another thing, I will be recording these sessions, so I will be posting this on a YouTube channel, so you can later watch there also. Okay, so enough talking, now we'll start with the questions. Huh. Yeah.
Bro.
So yeah.
So where we got link of YouTube channel, so
What?
link of YouTube channel.
Yeah, I will
Where,
share you. I
where
will share you that YouTube channel link, and even what I'm doing here, these slides also. I will share. I will give you some link for that also, so you can go through that also. Okay. So don't worry. Yeah. So I will post that in discussion forum. You can check from there those links. So yeah, we'll start with the first question. So you can read the question, and if anyone wants to answer also, you can answer in between. You can chat, you can write in the chat, you can open your mic, switch on your mic, and then also like tell about that. So whatever you want. If you don't know, then anyway, I will be solving that. So yeah, so the question is an emitter. So okay, just a quick recap. So we did studied about PMMC measurement like PMMC instruments. Then we went across its torque equations, like how it is derived, and then we went into electrodynamic instruments. So before that, PMMC instruments are used for DC measurements. It cannot measure AC. uh, then after that, talking about that, we went to electrodynamic instruments, and where like we changed the so there the magnet, like there is no permanent magnet. We can electrically we can generate that magnetic field, and then we derived that torque equations for that. After that, we discussed about the differences of these PMMC and electrodynamic instruments. So in these today lectures, the session, the questions will be mostly it will be based on the practical applications of PMMC instruments, because electrodynamic instruments, they are applied in like wattmeters and other things, but you will learn that later. So yeah, so then we talked about moving iron instruments also in those lectures. And yeah, then we talked about electrostatic instruments also, so their applications also will come later in these courses. And then we had then we talked about eddy current damping. And yeah, so like different types of torques and their equations, then ballistic galvanometer in the last lecture of those course, of that first week course. Okay. So now, so we'll start with this first question. So this is based on PMMC instrument. You have seen this in that lectures also. So I think you know quite about this. So yeah, the question is, an ammeter has a PMMC instrument with a coil resistance of, they are saying that the coil resistance of that ammeter is 99 ohms, and full scale deflection current is zero point 0.1 milliampere. So it means like for zero point 0.1 milliampere when we'll pass through it, so it will deflect fully. Okay. Then the shunt resistance Rs equals to 1 ohm. So they are saying there is a shunt resistance in this which is having a resistance of 1 ohm, and so they are saying determine the total current passing through the emitter at full scale deflection. So they are saying like when the emitter shows full scale deflection, then what is the total current passing through the emitter. Then if it is showing zero point 0.5 times of full scale deflection, then what is the current passing through it. And similarly for 0.25 fst. So just think of it, if you have any if you can tell something, anything, like don't bother whether it is stupid or not. Just comment if you want to, or if you want to switch on your mic, and you can say also. Yeah, whatever you want to say, just say whatever comes in your mind. How you will approach this? First of all, like how what you go for, how you like what is the idea you got in your mind when you saw this question? Just think. So see, so what the question is saying? Uh, so a PMMC instrument, first of all, PMMC instrument. So an emitter has been realized using an PMMC instrument. This is the important thing which you have to keep in mind. An emitter has a PMMC instrument. That means it can also have something else also. But for this thing, we are using PMMC instrument for deflection purpose. Okay. So because it can be realized from moving iron and others also. So now PMMC is being used to realize this emitter. So with the coil resistance of, let's say this, we have a PMMC meter here, and it's having a coil resistance of 99 ohm. So we normally denote the resistance of that coil like this in series with this. So this is like the instrument which is all the physics is going on, and then we have the coil resistance as 99 ohm for that. So now if we pass the current zero point 0.1 milliampere from this PMMC instrument, what's the first line is saying, then what it is doing, so this PMMC instrument is deflecting fully. That's what it signifies. Full scale deflection current of zero point 0.1 milliampere when is passed through that, then that is the full scale reading of this PMMC. Now they are saying they added one shunt resistance in this. Shunt resistance RF of like for, so till now this was PMMC instrument. To make an emitter, we added one shunt resistance in parallel to this PMMC instrument, and that was 1 ohm. Okay, so till now we had, yeah, till now we had this PMMC instrument with 99 ohm of resistance, and then we added a shunt resistance of 1 ohm to make it act as an emitter. Okay. But the question will arise: was it not acting as an emitter before this in this way? So it was acting as an emitter, but we will see the full scale, the full scale value, or the maximum value which this emitter can take now increased because of adding this 1 ohm resistance. So now, so this PMMC can take zero point 0.1 milliampere. So now they are saying determine the total current passing through the emitter. So at full scale deflection. So now when it is happening, like full scale deflection is happening, so we have zero point 0.1 milliampere of current. So we can calculate the voltage across this branch, and that same voltage will be dropping since these are both in parallel. So the same voltage will be dropping across 1 ohm resistance. So that will be the total current which is coming into this emitter box. So this is an emitter box. We can say emitter. Okay. So let's say we have this current as I minus 0.1 milli. So if we just equate the voltage across both the branches, then this will be 1 equals to 0.1 milli into 99 ohms. Okay, it's like this. So if we solve this, so we will get I as, I have written the answer, I can directly tell that. So this is like 10 milliamperes. So what is the observation we made from this answer? Initially, PMMC instrument was only able to measure this 0.1 milliampere of current. But what if we want to extend the range of this PMMC instrument? So for that, we introduced this 1 ohm shunt resistance by which For this full scale deflection, earlier it was zero point 0.1 milliampere only it can take, but now it can take 10 milliamperes of current. So basically we extended the range of this emitter. So the range of this range has been extended, we can say. Okay, by using the shunt. So till now it's okay. Similarly, we can go for zero point 0.5 full scale deflection and 0.25 full scale deflection also. So I think if somebody can solve it for B, it will be good. So if you can just solve, it's very easy. Just let me know what is the answer in the comments. Then we'll go to the next section. Next question, sorry. Just quickly if you can solve. Any answers? The formula is simple. So it's like E minus. So now it's we have zero point 0.5 times of zero point 0.1 milli. That is the zero point 0.5 times of full scale deflection. This is the current going through now the second this shunt branch. Then we have 1 ohm resistance, which is equals to zero point 0.1 milli into, sorry, zero point 0.1 milli, yeah, zero point 0.1 milli into 0.5 into 99. So this is B part. Okay, the answer is 5 milliamperes. So similarly, if we solve for like the third part also, then it will be I will be the same thing. It will be like 2.5 milliamperes. Okay. So, but the crux of this question, the understanding from this question we got is that we can increase the range of the full scale, increase the range of current for an PMMC meter by introducing shunt resistance across it. Okay, so this is done. Any doubts in this question? If no, we can go to next question. Yeah. So just read it. Just once read it. What this question is about? So the question is a PMMC instrument. Again, we are using PMMC with full scale deflection of 100 microampere. So full scale deflection is 100 microampere and a coil resistance of 1 kilo ohm is to be converted into a voltmeter. So earlier what we did, we converted that into an extended range of ammeter. Okay, but now we are converting this into a voltmeter. So, and how we are doing, the question itself is saying by introducing a coil resistance of 1 kilo ohm in series with this thing, PMMC instrument. So determine the required multiplier resistance. Oh no, it hasn't said that like yet. So yeah, so it's just saying we have to just convert that voltmeter, that PMMC instrument into a voltmeter. So how we'll do that? So that it is asking. So determine the required multiplier resistance if the voltmeter is to measure 50 volt at full scale. So when they say multiply, so we are adding that in series, that resistance, to convert it into a voltmeter at full scale. Also calculate the applied voltage when the instrument indicates this, and this times of full scale deflection. So first of all, just to tell you what is like so how this thing is being done. So we have a PMMC instrument again. The coil is having 1 kilo ohm of resistance. This coil. So this was a PMMC instrument. PMMC. This was a PMMC. Okay. So, and the full scale deflection, it gets when it is having 100 microampere of current through it, when the 100 microampere of current is passing through it. Then So if you want to measure a voltmeter, which is having 50-volt full scale reading. So right now, just see, okay, because some voltage is being dropped in this coil also. Oops, sorry for that. So yeah, so some voltage is being dropped in this PMMC instrument also. Okay, so what is that voltage drop? That for full scale deflection, if we say, so it is simple: 100 micro into the current passing through this branch into the resistance, that is 1 kilo, which is for how much? uh, 100 into 10 to the minus 3.1 volt. Okay. Yeah, calculation right. So it is zero point 0.1 volt. So only a zero point 0.1 volt drop is being so there's only zero point 0.1 volt drop across this PMMC instrument. So what we have to do in order to realize a voltmeter from it? So if we can introduce one resistor here, that is like we don't know. Yeah, we don't know the value of the resistance, and if this same current is passing from this PMMC instrument and then it comes here 100 microampere, it passed through it, then what is the voltage drop across this now? So this was the voltage drop across this much. Now what is the voltage drop across this? It will be, as the question saying, it is 50 volts. See, from zero point 0.1 volt we have extended the range of that voltmeter measurement to 50 volts by just introducing a resistor RS in series with this voltmeter, in this with this PMMC instrument. So this whole thing is now a voltmeter with a range of measuring 50 volts for full scale deflection, that is 100 microampere current. So this whole voltage is 50 volts, whole voltage drop, and the drop is, we can simple use 100 micro into 1 kilo. Yeah, 100 micro into 1 kilo plus 100 micro into RS. So we can easily solve RS from here. Okay, so the RS value will be what? RS will be 499 kilo ohms. So we need this much large resistance in series with this PMMC instrument to convert this into a voltmeter. Okay, this much, I think this much is correct. This much is okay. Lots of people have me. So till now, I think it's fine. I think someone can say yes in that comment section. Somebody please say yes. Anybody can say yes if it's fine till here. Okay, thank you. So now, we have this, and now so we got this RS. So now the question is very easy, and also calculate the applied voltage when the instrument indicates zero point 0.8 of full scale deflection. So now first part is in that, so this was the first part, so let's say second part is for zero point 0.8 full scale deflection. So now the current is, instead of 100 microampere, it's zero point 0.8 of 100 microampere, there is 80 microampere. So then what will be the applied voltage when the instrument indicates so what is the voltage drop then? So we have we have 80 micro into 1 kilo plus 80 micro into 499k. So we'll get the voltage drop as 40 volts. So when we are giving a zero point 0.8 zero point 0.8 times of full scale value of the current, then we are getting 40 volts of voltage drop across this thing. Okay. So now so similarly we can go for zero point 0.5 and 0.2 readings also. It's just mathematical calculations. I will not solve that. So we'll move to next question. So yeah, please read it. So this question is telling about a series ohm meter. So we saw that PMMC can help us realize ammeter. PMMC can help us realize voltmeter also. Now can PMMC help us realize ohm meter? So this is one example of that. How? So this, in this question, in this diagram, we can say this is a PMMC instrument, PMMC, yeah, PMMC meter, and by that we are trying to measure this resistance. This we have a known resistance. and this is a standard resistance which we used, we can say, for calibration or something. And then this is a meter resistance, which is the coil resistance basically. So here we are realizing, so but for series ohm meter we need this source, this battery source, for that to realize this thing. Then only we can measure this. So because we want to we need to like inject some current in through that resistance, and then we can say okay, this is the thing. So now yeah, the question is, a series ohm meter in figure is made up of 1.5 volt battery. So we have EB equals to 1.5 volts, 100 microampere meter, and a resistance R1, which makes, so they have said that RL plus RM equals to 15 kilo ohms of resistance. And so they are saying, first part is saying, determine the instrument indication when Rx equals to 0. So when we are just shorted this wire, this thing, we don't have any instrument, we don't have any resistance to measure. So then what is the yeah, so what the instrument will be deflecting, or instrument will be indicating. So they are asking this thing put to us. So in this case, so we have for first part we have EB, we know the total resistance of this branch is what, Rx is 0, so it will be, otherwise it will be it would be Rx RL plus RM. So we are just calculating the current through this branch, this I we are calculating, so this is I. Okay, so so that will be what we have, 1.5, we have 15 kilo, since Rx is 0, so it will give us zero point 0.1 milliampere. So that means when there is no resistance here, when there is no resistance to measure, when there is no resistance to measure, then what is happening, then the current is zero point 0.1 milliampere through the meter. So is this the full scale deflection current? So just say that, just see that this R1 is constant, this RM is constant. Okay, we cannot change that. But Rx is the measured, is the resistance to be measured. Okay, so then if Rx is 0, that means no resistance, and if no resistance, then like by theory, the current will be maximum in that branch. So this if this value is 0, then this will be maximum. So we can say, in other words, when Rx is 0, so this thing is the full scale current, full scale value of this meter, like this much is the full scale current value of this PMMC meter. So when Rx is 0, so now we determine, so I think this is clear for you. If not, you can ask me anytime whenever you want to. So this is okay, this is, now we got, this is the full scale current of this PMMC meter. One understanding what we got from this first part. Then the second is saying, determine how the resistance scale should be marked at zero point 0.5, 0.25, and 0.75 full scale deflection. So now so what we realize from the first part is that for Rx equals to 0, we are getting full scale deflection. Okay, so let's say this PMMC meter, which starts from 0, ends at some full scale deflection. So when it shows, when the needle deflects till here, it comes here. So that means this full scale, we can mark this as Rx equals to what? 0. Okay, so similarly, if zero point 0.5 full scale deflection is there, so how much will be the Rx value? So for that, we can simply, again, we can do that. So we have EB is constant 1.5 divided by Rx, we don't know. This part we know. Now since it is zero point 0.5 times of full scale deflection, definitely there is some resistance which has been introduced in this branch. That's why the current have been reduced. So we have Rx here, we have 15 kilo ohm here, that is that constant thing. And then they are saying zero point 0.5 times of full scale deflection, so that is 0.1, 0.5 times of 0.1 milli. So if we solve this, we got Rx as 15 kilo ohms. So that means when it is half at this point of that uh, deflection, so then that means Rx was 15 kilo ohms. Similarly, if it would have been at the 0.25 times of the full scale deflection, so I'm just skipping the calculation part. it is the same thing. So then Rx will be what? Rx will be 45 kilo ohms. So that means when it will be here, it will be deflecting here, then this will be 45 kilo ohms. So in this way, we realized an ohm meter using a PMMC meter. So this is another application of a PMMC meter. I think this is also clear to you. This is also simple only, but just an application of how we can use PMMC meter. Okay. Any doubts?
No, sir.
Okay. Thank you. Yeah. So this was a great question. So now we are moving to next question. So just read this question and tell how you will approach this. You can comment also. Just one word comment is also fine to start the approach. So the question is saying the sawtooth voltage waveform. So we have a voltage waveform like this. So we somehow generated this voltage waveform, and then we fed it to a moving iron voltmeter. So now it's saying the question is simple. Now it's saying what will be the reading of that. So before that, I want to ask you one again. Okay, 100 volt. Okay, I'll just check whether the answer is right or not. But the answer whether it is right or wrong, you should tell me the approach. So you can write okay what you thought before giving this answer, or you how you calculated. If the approach is right, then answer maybe doesn't matter if answer is right or wrong. It will matter, but right now approach should be fine. But I want to say answer is wrong. So see, when we are talking about moving iron voltmeter, so maybe you can correct your approach. So what it measures? So just recall your lectures and just recall that what this moving iron voltmeter or moving iron instrument we saw there, what it measures. Okay, first of all, the expression of that was what? I square, directly proportional to I square. So later, then we came to know in the lecture also, in the lecture itself, then that if you average it out for like high frequency calculations, then this will be directly proportional to the RMS value. Okay. It will give the RMS value of that. If we take the average of a square quantity, that is the root mean square. So that is the basically we are calculating the RMS value. So when it said it is a moving iron voltmeter, so that means it will be showing the RMS value of whatever signal is being passed through it. So here we have to calculate this signal's RMS value. Okay. So I think you have I don't know how you calculate this 100 volts, but we have to calculate the RMS value. Okay. So this should be the approach. So first we will see, okay, which is the instrument which is being used to measure that voltage. So whatever, irrespective of the voltage waveform. So you have already done your basics in maths, how to solve RMS average values of different waveforms, or if not you can practice also. We have many questions for that, but after that you should know, okay, if that instrument is there, now it's correct. Yeah, it is correct. The answer is correct, 57.94. So then so you should know then what is the instrument and how and what it will measure. So based on that you will calculate that value. So for others, for all of you, I will just tell how to calculate the RMS value of this waveform. So it will be, so we have, since we have the voltage VRMS, we can say square just to avoid the clumsiness. So 1 upon the time period we have, it is being repeated after 20 milliseconds, we can say 20 milli. Okay, integrate over 0 to 20 milliseconds. And what is this this thing? This is the equation of a straight line, y equals to mx, and we have that slope is what, 100 by 20 milliseconds. Okay. Oh, sorry. I think- yeah. and this is T dt. I think it's okay. So now if we just, and this is the square of this. So if you solve this quantity, I will not solve this for you. It's a math only. So if you solve this quantity, so you will get this value as 100 by 100 by 3 100 by root 3 square. So it will be like VRMS will be 100 by root 3, that is 57.73 volts. Okay, so this is, so you should know like, okay, which is instrument and how, then you will be knowing okay how you have to approach that thing. I think if this is fine, we can move to the next question. If any doubts. Okay, okay, we will move to the next question. Now this question, so we have the options, just tell me. Okay, yeah, just tell me what is the answer. So this is A, this is B, this is C, this is D. So it's showing three moving iron type. So iron type, voltmeters are connected as shown below. First of all, read the question carefully. I have made mistakes in my by reading the questions when I was, yeah, when I was in a BTech days, but you should read the question correctly. So yeah, three moving iron type voltmeters are connected as shown below. Voltmeter readings are V, V1 and V2 as indicated. The correct relation among the voltmeter readings is, yeah, you can write A, B, C, D. It's very easy to write any one of that four options. You can guess also. Yeah, I think, yeah, it's correct. D, okay. Others also have the same answer? Or they are like, they are getting something else? No issues. I will tell you what is the, like, how we'll approach this thing. So since we have moving iron type, so that is one thing. But if we are measuring a voltage across this capacitor or an inductor, so we know that it's fully basic. So we have this voltage. So the voltage from the main voltage in a capacitor, the current leads by 90 degree than the voltage. So that means the voltage lags. So if we have a current here, let's say, yeah, so we have this current, I we had. So basically, then with this current, this V1 will be lagging because this is a capacitor, and for this inductor, it is vice versa. The voltage leads with respect to the current, so this will be V2. So the net voltage will be the resultant of this, which is V equals to V2 minus V1. Is it fine? Did you all get this thing? If you will, okay. I think if it is fine, then we'll move to the next question. Yeah, okay, thank you. Yeah, so next question. Just read it. So the question is saying a periodic voltage waveform observed on an oscilloscope across a load is shown. So there was a periodic voltage waveform. It is being repeated after this 20 milliseconds of interval, and it observed on an oscilloscope. So this was being observed in an oscilloscope across a load. A PMMC meter is connected across the same load. So uh, we had this oscilloscope. So there was a, let's say there was a load. This was connected and being observed here, something like this. Okay, but at the same time there was one PMMC meter uh, which was attached to the parallel to this resistance also, this load. Okay, so this is what question saying. So now, so what does this PMMC instrument will read? What will this PMMC instrument will read? Any answers? So I will give you for those who want to get a hint or something. So it's a PMMC instrument. So you have to calculate the average value of the signal. So now you can answer. So just now tell me what is the answer. So I can tell you, if you want to go with shortcuts, you can go with shortcuts. Okay, one answer is 5 volts. Next, another answer. Any other answer apart from this? You can either go with the traditional proper the equation of that thing, the average value, average formula of that, like how you calculate an average of a signal, or you can go with shortcuts also. It's up to you if you know the shortcuts. But I will recommend before getting to know the shortcuts, you should know the fundamentals of that shortcuts. So yeah. So we have two answers, 5 volts and 4 volts. Any other answers? I think some yeah. So the answer is 4 volts. I will go with shortcut to avoid time, but you can go with the direct approach. So the shortcut is so if these are like proper shapes, triangle, rectangle, and yeah, rectangle. So like the area, if we calculate of this triangle, this, so we'll have to subtract this area from the above. So these are the things which are above that, above this thing. So the area of this triangle is what? Half into 10 into 10 minus. Now this area is in negative zone. So we will be having minus 5 into 2. This is time period is 2, plus we have 8 into 5 divided by the total time period, that is what? 20 milliseconds. Okay, so we had milli over there also, like here also milli will cancel, and so then we'll be having 4 volts as the answer. So yeah. Okay, it's also simple. Then, if I think beneficial means a DC quantity only. DC means average. So DC is what? When you say, okay, I will correct you on this. Hmm, how will I correct this? Okay, so let's say you said DC. Okay, so I will ask, what is the measurement? So this is the sinusoidal line. This is sinusoidal voltage, 5 volts and minus 5 volts. So this is being fed to the PMMC instrument. So what will the value of the what PMMC will be showing? You can write. You will get to know your answer with your like. So this will show 0. Okay, because this is like the amount of positive thing, the amount of positive was like the positive magnitude, and the amount of the negative it's same. But if we feed this thing to an PMMC instrument where it is not oscillating across around the 0 volt line, but it is oscillating across a 1 volt line. This is also AC kind of thing, alternate AC or like alternating current, but it is having one DC component also, so it will show 1 volt. The PMC instrument will show 1 volt here. So you are correct that PMC instrument measure DC quantity only. But then in this, since this we have what will be the average of the signal? So average will be like all the positive stuff. If you can go, if you vaguely say all the positive quantities, all the positive side signals, and subtracting that with the negative side quantities, so that will be the average. So its average will lie somewhere here, 4 volts. This whole signal average will be lying here. Is it clear to you? Okay, thank you. Now, next question. Yeah, read this. So a PMMC voltmeter is connected across a series combination of a DC voltage source V1 equals to 2 volt and a AC voltage source V2 equals to 3 sine 40. The meter reads. So I will go conventionally with this so as to make you understand about okay how things are going. So before that, any answers on this? I just told the answer to this question, like the concept of the answer to this question in the previous question. So you can get from that also. Ah, yeah, it's correct. Yeah, 2 volts, 2 volts. Others also, do they agree or they have something else? If they have, they can ask, they can tell. If yeah, okay. Thank you. 2 volts, yeah, 2 volts is the answer. So how we will be solving this? I will just solve that. Now I'll properly solve that. So the formula for average voltages or the average is 1 by T 0 to the whole time period 0 to T, uh, whatever we have V of T d T of T. Okay, this is the simple average, like to calculate an average of any signal or any quantity. Now if we just see how the signal looks like, so we have first 3 sine 40. So this is having 3, this is having minus 3, and it's oscillating based on this omega 4. Okay, and we have a 2 volt DC signal also. So this signal is being climbed up to this, and then we are getting this thing. So this is 2 volts being climb means being added to that signal, and then we are getting something like this. So this is minus 1 volts and this is 5 volts. Okay, I think this is correct, this is fine. So this is how signal looks like, but the PMMC will only measure the like the average of the signal. So it will be having this much of positive quantity, but at the same time it will be having some negative quantity. So it will be, if we analyze like this, so then this will be this instrument will be subtracting that negative quantity from this thing, and then we'll get the average that we say, what we say that the DC thing. And we already know that what is the DC value of this, that is 2 volts. Otherwise I will just solve for you. So this is the thing. So we have this thing. So we have 1 by T integration 2 plus 3 sine 4t dt. Okay, 0 to t. Then we have 1 by T. This will become 2t first thing. Then this will be 3 cos 4t divided by 4. So this will be 0 to t. Okay, and this we have already get given that limits, put the limits in the first part. So but now we know that if we so we if we put these two values, and then this will be like 1 minus 1, this will cancel out and this will be 0, we'll only get 2 here. Okay, it's fairly simple maths. So I think this is fine. So now then we'll move towards the next question. It's kind of a theoretical question. You can answer. Take your time. Answer whenever you like. Any answers or any comments on this? The effect of stray magnetic fields on the actuating torque of a portable instrument is maximum when the operating field on the instrument and the stray fields are parallel. Okay, one answer we got. Another answer? Any other answer? So, here, like the thing is simple only. So when we have when we have our magnetic field lines, let's say we talk about that PMMC meter. So we had this B, these the magnetic field lines in between these two magnets, north and south. Okay, so then what was happening? If we introduce, so let's say there was some extra magnetic field from some external from some external environment, a magnetic field came. So let's say it came like this, stray magnetic field, stray M. Okay, so it came like this. So so there will be some effect of stray magnetic field on this in this way, and also it can come like this also, and maybe like this also. But the maximum problem it will create or it will distort, but maximum when it will, because they are saying the maximum thing, it will be creating issues when the stray so this is our original magnetic field, and the stray magnetic field, if it comes like this or it comes like this. So we wanted to measure our thing with based on this peak value, but in respect of that, we also encountered these stray magnetic fields. So if the lines are parallel, either in the same direction or the opposite direction of that field, we will get distortions. Either it will add up to our magnetic field or it will decrease the magnetic field. Both things can happen. So the parallel answer is correct. We'll get the maximum deflections in that case, or we can say maximum errors in that case. Okay. Next question. Yeah, read it and then yeah. So sometimes like options are like this, so you can answer based on the options also. That is a good thing when you don't know the concept, but if you know the concept, then you should you should be confident about it. Otherwise, the technique of like removing the other options also works sometimes. But then also like, okay, one answer we got, three answer. Okay, any other answers? Anyone wants to deviate from this or wants to be favor? I think three. Okay, three. Getting three. Two answers for three. Any other votes? Yeah, I think the question is it's straightforward. It's saying that eddy current damping. So we don't use for as we saw in the lectures also. Yeah, three. Yeah. So so we saw in the lectures also. So when we have an iron core and it was like this something, and then we had one iron bar here, and if you talk about the repulsive one, it can work for both of the case. So so this N and south, these were being induced here, and these poles were being induced in this iron core because of this current being fed through this coil, and then it passed through this. So this happened. So now if we use eddy current damping somehow, so eddy current damping will be having its own magnetic field, so which will like create issues in these actual magnetic fields, which are being used by this iron bars to get their polarity and then show the deflection here, so that we don't want. So that's why in moving iron type instruments we used frictional damping, air friction damping. Yeah, air friction damping we used in this moving iron. But in case of PMMC, we use, so that's the add-on to this question. In case of PMMC meters, we use this eddy current damping because there we are using that motion of that coil. We are actually taking the use of, we are actually exploiting the use of that movement of the coil. So once the movement is there, so this movement, and we have flux already, so we had that aluminum on which the coil was wrapped. So that aluminum will induce one EMF like across it, and because of that there will be like opposite torque from which it from where it got its origin, like from where it got that induced EMF. So it will oppose that torque which was actually making the coil move. So in that case it is helpful, this eddy current damping. But in this case, since there is no movement like this in that, so we cannot use that movement of that coil in this case. So is it clear explanation? Okay, okay, okay. We'll go to the next question. If I have any doubts, then you can just interrupt me in between. Yeah, next question. Just read this question. You can take time if you want. It is quite a big question, but yeah, I need answers. So what will be the answer for this? Take your time and then tell what can be the answer. So the question says that a rectangular wave. So first of all, there is a rectangular wave passed through PMMC. Then it reads R1. Then we have a sinusoidal AC. It is also being passed through PMMC, and we have a reading of R2. And then we pass a square wave through a moving iron instrument. Then we have R3, and then a sinusoidal AC moving through or passing through this moving iron. Then we have R4. Okay, so we have PMMC here, we have moving iron here, and then we have a rectangular wave like this, kind of this, and then we have a sinusoidal AC wave, but that is full wave rectified. So okay, by the way, full wave rectified means like the negative quantity of that signal has been converted into a positive thing. I think you might have read that thing, but some of you not. So just clarifying. So after rectifying a sinusoidal wave, we have this thing. So you will learn in this course also. There are rectifiers instruments, so like rectifying instruments also. So using diodes. So this is one thing. Then we have in moving iron, we pass a square wave. Then we also passed a sinusoidal AC waveform. So this is R1, this is R2, this is R3, this is R4. Any guesses? I think you should not guess, you should solve and then properly say. B option. Okay, we got one answer from one student. B option. Any other answers? Others can also tell. It's good to practice questions. It will help you maybe for competitive exams or like even your semester exams also, and in this course also, for this course also. Okay, one more answer we got, B. Any other people trying? Wait for just 1 minute and then we'll answer this. Yeah, yeah. Okay, we get another answer as B. So I think B should be then correct. Yeah, B is correct. So yeah, so it's simple. Again, we have PMMC, so it will calculate the average value, and then we have MI. It will calculate the RMS value. Okay, so they mentioned if all input waveforms had equal peak values and the correct magnitude of measurements are arranged in the ascending order. So like the highest magnitude which we'll get. So they only said okay. Oh, sorry, it's rectangular wave and passes from AMC. AC. Okay, they didn't mention this thing. Okay. So if it is rectangular or like a square, we will be having the same like the same value for average. I think the same average value if their peak is same. So for this, so yeah, first of all, this R4 we will be having an RMS value that is V by root 2. For this RMS, we believe if it is having a V amplitude, it will be having V as a RMS value. This average and RMS like it's same, so this will be V also. If this is V, and for this thing, this will be average. So this is 2Vm by, so 2V by P by V by pi. So these are all based on the standard foundational question like formulas of average and RMS values. So yeah, so this is if this is V, so this is yeah 2V by pi, 2V by pi. So so we know definitely R1 equals to R3 will be at the top. Then what we will be having R4, so 1 by root 2 is more than 2 by pi, so we'll be having R4 here, and then smallest will be R2. So B will be the answer. Okay, now okay, so these, and then we'll move towards some questions from previous year. So this might help you in solving the assignments. So yeah, so I think this somewhat you encountered in your assignments, but these are different, but the concept is almost same. So first of all, any doubts in when you went through the assignment questions? Did you face anything? Or before this? Or okay, yeah, just tell me if you faced any in any particular question, if you faced anything like any doubt. You can just mention that question name. I can give you hints on that, but I will not solve for you because the due date is still to be over. But I can give you some. I can help you with something. You can just write the question number for first week assignment. I'm talking about. Yeah, just think if you just go through whatever you did and just let me know. I'm waiting. If not, then we will go to the some other questions. Not these. We'll go to some other questions. Yeah. Just go through what you did and then just let me know. I think you have solved all the questions from week one, and you got the right answers also for that. Nice. So if you come to know like later in this session, then you can also tell me then, like you had good doubt in this question, so I'll tell you then also. Or anyway, discussion forums are there, so you can ask. So now just so I would have done this like before those questions, but just to revise your concepts. So I will be going through these basic questions of this. For this course, and yeah, it will be good, it will be a good revision for you. So but you solved already like good questions, so these are also good, but okay, it will just help you in practice. So yeah, first question: consider a full wave rectified sinusoidal voltage signal as shown below. If the RMS value is 10 volts, okay, they have said VRMS is 10, then calculate the average value. Okay. Can calculate the average value. So if we have RMS values, and then what will be the average value? So I think for like okay, I will give you one, and for next class, okay, 14.14 volts. Okay, okay. Any other answers? Any other guesses or answers? So we know for this kind of signals we have Vm by root 2 is the this thing, your the value of the RMS value of this signal, or we can say this is basically sinusoidal signal, because RMS value of this and this will be same. Okay, so and we know this RMS value of a sinusoidal signal is Vm by root 2. If not, you can just go with that basic formula, and you will get this Vm by root 2. So we know Vm by root 2 is 10. So now V average will be what? So V average for these signals, you should remember this: 2 Vm by 2 Vm by pi is the direct answer for this. So it will be good. It will be good if you remember this thing. Like straight away you can answer this thing. So to Vm by pi, otherwise you can go with the proper foundational thing also. And so based on this, so we know this Vm we can get from this formula, and then we can put this and we can get the answer. Okay, I think yeah, 14.14. I don't know the calculation, but okay, wait, I will calculate it. Okay, we can calculate it here. 10 root 2 into 2 by pi. So what will be the solution? 2 into, yeah, I think it's 9. Maybe I think you did some mistake in calculation part. I think 9 is the answer. Yeah. So moving to the next part, consider half wave rectified signal. So this is half wave rectified because we only have the positive peak. We don't have this one. And so if you want me to go through proper steps in this question, then you can ask me. Okay. Yeah. So next question. Consider half wave rectified sinusoidal signal as shown below. If the RMS value is 10 volts, then calculate the average value. Okay. Yeah. 9 volts. Okay. Good, good. So then, yeah, next question. Moving to the next question. Yeah, again, I will give you some 1 2 minutes. Just let me know what is the answer for this question. Others can also solve, and then they can tell. So if you will not solve these questions while we are having this live session, so you can get bored while these live sessions are taking place. But if you solve this, then time will pass like anything. So it's your choice if you want to get bored or you want to solve it, so that you can bear mm, this time with me. Any answers on this? So yeah, so for this, like again, the fundamental thing is to go with that proper formulas, but instead of that, or I will just write that formula for you. So if the RMS value is 10 volts, so we know that. So what is the RMS 1 by T? So let's say if we so this time period is T, okay. So here this time period is T because it is repeating after this thing. So we will have from 0 to T, and this is in sinusoidal signal. So let's say its peak is Vm sine omega t dt, okay, or it is square of this quantity, and then we have RMS value square, okay. This is the basic thing everyone knows now, but this is 0 for this, so we can only integrate this for t by 2 time, and we will have Vm sine omega t dt, okay. So when we will be calculating this, we can take Vm out. This will be cos omega t divided by omega, since we are integrating respect to time, and we will have 0 to t by 2 here, okay. Vm by t omega here, and then we can substitute this in cost. So this will be 2 pi by t into t by 2. So this will be pi, so it will be 2 here. You can just put t by 2 and 0 here, and then you can add that, and then you will be having this one. So this will be 2 pi, okay. uh, oh, okay, so sorry, this is square now. Okay, sorry. So this is square, okay. So this will be 1 by t, 0 to t by 2. This will be Vm square outside. We will have, so sine square omega t can be written as 1 minus cos 2 omega t by 2 dt, okay. So this will be Vm square by t, 0 to t by 2. So if we integrate this constant thing, so it will be t, oh sorry, small t by 2, and if we integrate this cos 2 omega t over a period of t by 2, we will get sine 2 omega t by 2 to the 4 omega, and we will have 0 to t by 2, okay. So now if we substitute this, so what we will get, this is omega 2 pi by t into t by 2, 2 pi. So this will be sine 2 pi and sine 0, it will be 0, this whole quantity will become 0, Vm square by t. This will be t square by 4. Okay, 0 0. Sorry, t by 4 t. I'll just, yeah, so this will be Vm square by t. So this will be t by 4. Okay, and this will be this Vm square by 4. So this is Vrms square, and then we'll get Vrms as Vm by 2. Okay, so this is the RMS quantity of a half wave rectified signal. Vrms equals to Vm by 2. Okay, if I am correct, just adjust. Yeah, Vm by 2. Now we have, so they said the RMS value is 10 volts. So this Vm by 2 we have as 10. So we can get Vm from here. Okay. Then calculate the average value. So average value of this is, since for full wave we have 2 Vm by pi as an average value. For this, the average value is Vm by pi. Again, we can go through that same formulas, but yeah, you can derive it. So if you don't get to know, so if you don't get these formulas when you will be deriving back at home after this lecture, so then you can just tell me in the next session. I will derive it for you, no issues. Okay, so this is Vm by pi for half wave rectifier signal, and we can get 10 by pi here answer. Okay, so you can go through all these things. If you find any difficulties, anything in any part of this video or lectures, just in next session also you can tell me, no issues, we'll go through it. So now the third question. Okay, yeah, third question. I think this I think this yeah, this should, many of you can answer this, so just I need some answers from you. For the circuit above, the Thevenin voltage and Thevenin resistance across terminals respectively are. Yeah, I'm expecting at least some answers from you, from your side. I think you know about this Thevenin resistance and voltage concept. Yeah, I think it's there. We know. Yeah, we learned this in, I think, first year of BTech. So these questions are kind of warm up questions, so that you can get started yourself with this course. So I think I already gave that proper questions initially, but I would have gave these questions initially. But never mind, we can practice still. So for this, like it's the question for this, like for the circuit above, the Thevenin voltage and Thevenin resistance across terminal 1 prime. So they are saying, so if we have to calculate RTH, the Thevenin resistance, we can just short the all the voltage source and open the current sources, or like open circuit the current sources. So in this case, for Thevenin resistance seen by this thing, we will have 2 ohms here, 2 ohms here. So what is the RTH from here? It will be 1 ohm. Okay, and for Thevenin voltage, it is the voltage drop across 1 prime for a proper this for the this main circuit. So this is 2 ohms. So you can use any technique. 1 ohm, yeah, okay, yeah, fine, 1 ohm. Okay, so you can tell me like what is the VTH. So VTH is this one, VTH. So yeah, tell me, so what will be the VTH? Now I have given this much and you can answer. Now I need answer from this, from your side. So whichever technique you want, KVL, KCL, whatever you want to apply, you just apply. And what is VTH? So we can get the current from this branch, that is, so this is VTH. So we can get the current simple 10 by 4, and then the voltage drop will be what? Across these 2 ohm resistance, it will be 2 into 10 by 4. This will be VTH. Okay, 2 5. So this will be 5 volt with the VTH. So this will be the answer. Ah, nice, correct. 5 volt 1 ohm. Okay, now the next question. So a current carrying wire of length 20 centimeter. So this is the that wire. So current is going downwards. This convention, this cross is, that means it is going downwards. That current from that length. So it is like yeah, something like this going inside the screen. So the wire of 20 centimeters placed in magnetic field of 0.5 T. Calculate the electromagnetic force if 2 ampere current is flowing through the wire. So we have current which is being flown through this. So they are asking for force. Force is BIL. What is B? Yeah. So force is BIL. B is zero point 0.5. We have current as 2 amperes, and we have length as 20 centimeter. Just changing into SI unit meter. So this we can get. What is the answer? Yeah, it will be zero point 0.2 newtons. Okay. It was simple, straightforward. Now, yeah. Okay, I thought it's some doubts. Yeah, so for next question, what is the direction of the force? Calculate the question 4 above. So this is the question. So what is the direction of the force? So we know there is a current carrying conductor in magnetic field. So what is the direction of the force? First, you can tell which hand, which law you will be using, which Fleming's law you will be using to get the direction. So the if you have seen this, so the options are towards left, right, upwards, downwards. Any answers? Uh, if option A, okay, towards left, okay. Any other answers? Upwards. One more answer, upwards. Okay. Another any other answers? So can you tell me which law which Fleming's rule you used, or like any other rule you used? Is yeah, left hand rule, yeah, it will be there. So using left hand rule, I think it should be downwards, but we will check it again. So the answer is downwards, but we'll see how it is. So Fleming's left hand rule, so we have so current is flowing downwards, okay. So we have magnetic field lines. So this is magnetic field lines, and we have current. Okay. So this will be the force, okay. This will be the magnetic field line. So magnetic field lines are this side. So if I see like this, so it's the current is downwards, field lines are this, so it will be downwards. the force will be downwards. Okay, so yeah, so the force will be downwards in this case. Any objections on this? If no, then we can proceed. Okay. Yeah. So next question: a current carrying conductor of length 10 centimeter is moving at a constant velocity of 5 centimeter in a magnetic field of this 0.8 Weber per meter square. What is the magnitude of the induced EMF in the conductor? So this is also this, I think, all the basics of magnetics. So induced EMF is what is it is like BVL, and we can substitute everything and we can get the answer. It's simple. Okay. Now the next question is the question 6, for the induced EMF, which side has the positive polarity? Which side has the, so yeah, so that means you once you want to, now you should tell me the direction of the induced EMF. So here, as we used earlier Fleming's left hand rule for getting the force direction, but now we have already the conductor is moving inside that magnetic field, it is cutting those magnetic fields, and now what is the what is the direction of the induced EMF? So here we will be using Fleming's right hand rule. Okay, and then you can answer that. So we have the force direction this side, and sorry, force direction downwards. We have uh, field direction this side, so I think it will be upwards towards the reader should be the answer. uh, like anyone wants to object that, like I'm getting side, I means closer to the reader means towards us. So again, so we have force is downwards, we have this magnetic field lines this way, and we have, so it will be towards me, this current, this. So yeah, think this is also simple. So now this question: what is the value of x at the balance condition of the bridge? I think this everyone can tell. Yeah, yeah. Any answers? Three. Okay, three. One answer. Any other answer? Fast, fast, fast. This is very easy. Three, 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 three. Okay, three. Yeah, three is the answer. Correct. It's simple. So we can have 4 by x equals to 8 by 6. 2, 3, x equals to 3. Okay. Now next question. I think this will make you remember your 12th class. It's also easy. You can tell. So this we have like potentiometer. I think you all have seen this in, not in BTech, but at least in your 12th class you have seen this. So in the above figure is balanced at the length of 75 centimeters. So this galvanometer is showing no deflection at 75 centimeters such that no current flows through the galvanometer G. Then determine voltage E. So this E will be the voltage drop across this wire, 75 centimeter wire. Okay. So if we have a current of I here, so and if this wire is directly proportional to its length, so then the resistance of this wire is directly proportional to its length. So this 75 centimeter resistance will be directly proportional to 0.75, we can say, in meters. I'm just talking. So then so we have the voltage drop, which E, it is equals to I, that is the current flowing through this I, this is I, into it is directly proportional since we don't know the proportionality constant, so this will be 0.75. Okay, and we also have this 10 is directly proportional to I current and the total resistance of this thing, that is 1. Okay, if we divide if we divide both of this, then we will have 0.75 by 1, we'll have E equals to 7.5 volts. Okay, 10 volts. Okay, 10 volts. No, 10 volts is not. It's 7.5. Just I think calculation mistake. That's all. No issues. Yeah, if you just check your calculation, I think then it will be fine. Okay, so with the potentiometer of the, okay, so this was figure is balanced. Okay, then no current flows. Okay, then determine voltage E. We have this one. Now next last I think is this. Yeah. Yeah. In the above figure, the current through RB is to be measured. So this RB, if the current, then the correct way of connecting an ammeter is again. So this I think I'll just reduce this much is fine. So what is the current way to connect an ammeter across this RB? So all these are basic measurement fundamentals which you should know, and I think you know that, you have read that in your, I think, BTech 12th, wherever, like, so yeah, of connecting an emitter is, so will you be connecting this in series with RB or parallel in RB? Okay, only two options are there. It's easy for you to answer now. B. Okay, one answer B. Okay, another any series. Okay, that means you are saying A. Okay, series. Okay, any other answer? B. Okay, one more answer B. Okay, any other answers? Any other guesses? Only two options. 50-50% chances of getting your answer. Okay, we have two B, one series. Mm-hmm. So the answer to this is A, because this emitter is having, so as I talked to you in earlier classes also, not earlier class, sorry, initially in the lectures, so we connected one PMMC and we made it an extendable emitter by connecting an shunt resistor across parallel to this. So just connect these things. So if you start doing this, so then it will be a lot easier, much easier for you to like answer and clear your concept. So we connected a 1 ohm resistance across it. So that means normally this ammeter, so this we how we made an extendable range ammeter. So that means we made one ammeter. So we had this much less resistance, 1 ohm, which was making that ammeter works as an ammeter. Okay. Now, if we connect emitter in parallel with this, and it is saying that we have to measure the current through this. So first, say we had current through this as I here. Now, if we connect, let's say we'll talk about this first. So if we connect, so I was here. So this is the new part which has been added here. So now this I, so let's say this RB was some value. Let's say even if it is 1 ohm also, and this emitter will so these are two in parallel, so the resistance, the maximum resistance which can show in a parallel combination is the minimum of that of both of them. So this is 1 ohm, so this will be showing 1 ohm. So current will see, okay, 1 ohm is here, also 1 ohm is here, I will divert myself, I by 2, I by 2. So actually the current which we wanted to measure, original current was I, but now we are only measuring I by 2. So sorry, this I by 2, the current from the ammeter, so it's half of the what we wanted to measure. So that's why we should never connect this ammeter in parallel to whatever we want to measure. Ammeter is connected in series and volt. Yeah, yeah, it is correct. So why so when we write, when we say this line, as Atul said, why we say this, because the shunt resistance of the emitter, or the emitter, or we can say equivalent resistance, is very less. So if we connect something parallel to the load, so then this loading, so this is what loading is. This is the loading effect. Okay, this we say as loading. So this emitter loads this RB. That means this, and what we wanted to measure, we wanted to measure I, but instead of I we measured I by 2. That is loading. But in this case, this was 1 ohm, current was I. Okay, and let's say this was 1 ohm. So although, but now from here it will be like let's say it was I prime, although there will be some like it cannot be same, because now the total resistance is 2 ohm instead of 1 ohm here. But still it will be much more, much better than this case. Got my point? So that is one thing. So anyway, but for very small values like 1 ohm, I just took as an example. But for very small values we have we have other techniques, but for just example sake I used 1 ohm. Okay, so this is the case. So for the shunt, because of the shunt seen in the ammeter, that's why we connect it in series. But in voltmeter we connect a very large value of that multiplier resistance in series with that in the voltmeter. So that's why the voltmeter resistance is very high. So that's why voltmeters are connected in parallel, because in parallel if it is connected, no current will go through that. So that's, it's fine I think for voltmeter. Now the next question. In the above figure, if the voltage across R2 is to be measured, then the correct way of connecting a voltmeter is. Now, okay, I gave you answer for this in the previous, so I expect everyone should answer this correctly. So only two options, but now the probability of answering correctly is I think 70-30. B, okay. Mm-hmm. B. Okay, two B's. Any other B? Ah, okay, yeah, so you got the point. Okay, so B is the answer. Connected B because we connected in parallel because it was having very high resistance. And even if it is, so let's say it is, we calculated 499k in one of the previous questions. Let's say it is 499k. So most of the current will be passing through it. It will not go through a very high resistance path. Okay, less current will go, but it will not go. Mostly it will go from this one. But one thing to keep in mind, loading is happening here also, because nothing is ideal. That you will see in later lectures. Even if it is having 499k, then also loading is there. But it is much better than this scenario. Okay. So I think you got my point. So next question. An ammeter has an internal resistance of 1 ohm and it can measure up to 5 amperes. If one needs to measure 10 ampere current, then how much shunt resistance needs to be added? So all things which we told in, I think, one of the starting questions of today's session. So that's what it's being concluded here in this. So you can now tell, okay, so we have an ammeter of internal resistance. That means now they are directly saying, okay, they have an ammeter which is having an internal resistance of 1 ohm. That is indirect. That is one way of saying we have a PMMC meter which is having a coil resistance of 1 ohm. So you can say it as 1 ohm. Okay, now I think you can connect all those things. Okay, 5, we got one answer. 5. I'll just check if it is 5 or not. Okay, we got 1 5. Okay, any other answers? And it can measure up to 5 amperes. Okay, 5 amperes. Now if one needs to measure 10 amperes current, so they are saying if we get 10 amperes, so how much shunt resistance we should get? So it's simple. So 10 amperes we are having, 10 minus whatever full scale current we got here, that is 5 into Rs equals to 5 into 1. So voltage across this branch is equals to the voltage across this branch. So we will have Rs equals to 1 ohm. I think some calculation mistake in your answer, but I think 1 ohm is the correct answer. But I think you got the concept. So yeah, if this is fine, then we can move to the next question. Question 13th. So now they're talking about voltmeter. So now you can, I think, answer correctly. So what will be the answer? Just tell me. So for your convenience, I will just give that thing. So this is PA. So we have a voltmeter with internal resistance of 2 kilo ohm. Okay, and then it can measure up to 5 volts. So this is being measured as 5 volts. If one needs to measure 25 volts, now we need this to measure 25 volts. How we can make the voltage drop? By using a resistor here, RS. So here was 5 volt drop, so here it will be 25 volt drop. Then how much series resistance is to be added? So this they are telling us to answer it, asking us to. 8 kilo ohm, okay. One answer. Any other answers? I think this easy, and 8 kilo ohm is correct. 8 kilo ohm. Okay. Yeah. Now this question, 14th. So I think have you read this op amps? You can, if somebody have not read this thing in your BTech or MTech, like whatever, you can say just you can just type no if any one of you have not read about this op amp. Okay, so people are there who, okay, no issues. So we will skip this. Should we skip or should I tell you this? Okay, for others also I can, for just for like, so okay, I'll just so this op amps are basically we will talk about this much in details later on this in this in this course. I think in lecture in week 7 or 8. But for now being, I'll just tell you. So what is the application of op amp? So it basically amplifies the differential voltage. So whatever we have, let's say we have one voltage here at this terminal, that is plus side V1. We have one voltage V2. So this V0 will be some amplification which it will be doing A into V1, that is V1 positive side voltage minus V2. So this is the work of this op amp. Although I'm saying very in a very crude manner, but you can say it is the work of this. And this happens only when, and this happens, and this gain is open loop. If this gain is open loop gain, I will say why. If this is open loop, if this is open loop gain, that means there is no feedback. If there would have been a feedback, this would have been look like this. Or we can say either something, so this is a feedback to this, or we will be having something like this, some resistance or something like. So then it would be a gain which this will be showing, then it would be an closed loop gain. But if these are not there, these things are not there, no feedback is there, then we will have this open loop gain. We will not have closed loop gain. So in this case, we are having this as open loop. This is acting as an open loop differential amplifier. So and this open loop gain of an op amp is normally very high. I think if we talk about this your it's I think 70 to 80 dB. We can, so dB is the normal value which we talk about for the gains. So 70 to 80 dB, which is having a nice gain of op amp. We call it as a nice open loop gain op amp. So and it's very large. So if we convert this into, so this is a log scale. So if we convert it into actual quantity, then it will be 100 200,000 or something like that. So that makes this op amp goes into saturation. So in saturation, that means it will either show only plus and minus 12 volts. That is the supply of this. So it will not act according to this, it will act according to these things. Okay. Now the polarity of this will be decided based on the polarity of the difference of these two. So V1 minus V2. So which is bigger in this case? So V1 is what? Minus 2, because we have opposite polarity here. V2 is what? Minus 1, and we have minus in between. So we have ultimately a negative thing here. at the inputs of this op amp. So that means we will get V naught as minus 12 volts. Okay, no need to worry if you didn't get anything from this. You will get to know about this later in the lectures. For those who knew this, so minus 12 volt is the answer. Okay, no need to worry. Then 15th. Okay, welcome. The decimal equivalent of the binary number is, so this is very simple. I'll just tell you 1 into 2 3 plus 0 plus 1 into 2 plus 1, 0 into 1. So this will be 9 10 10 volt, 10 will be the answer. Okay, is easy, very easy. 10. What is the maximum value that an 8 binary number can take? uh, this is also very easy. So it is 255. So that is 2 to the power 8. Yeah. Okay, 255. Correct. An inductor having an inductance of 3 milliampere carrying a current of 2 ampere. The electromagnetic energy stored in it is fast. So this, the formula is half Li square. Simple. So this is all like to recall your basics. Half into L, we have 3 milli into 2 to the 4. We'll get this as 6 millijoules. Okay. For inductors, so inductors, they store energy as magnetic, yeah, correct, 6 millijoules. Next question: a capacitor having a capacitance of 200 microfarad has a voltage of 10 volt across it. The electrostatic energy stored in it is, we talked about inductance earlier, now we are talking about capacitance. So it will be half cv square. Okay, so you can just put the form values and you can get the answer. The answer will be uh, yeah, 10 millijoule. 10, I think. Yeah, I think some that mistake. Maybe I think this is micro, so maybe that's a point. Instead of 0.01, it will be 10 millijoule. Oh, 0.01 it's coming. Wait, I'll just check. Hmm, I think it will be 10 millijoules. Yeah, it will be 10 millijoules. Just check once. I think it's just calculation mistake. Okay. So if that is fine, then we can move to next question. Find the electromagnetic energy stored in the above circuit. This is also very simple. We know for inductance it is half L1 I1 square plus half L2 I2 square plus, for mutual inductance, 10. Yeah, 10 is fine. Yeah, okay, I'm going too fast. 19 question. Yeah, you can read the question. Find the electromagnetic energy stored in the above circuit. So we know the energy stored in an inductor we just saw, half Li square. And then for mutual inductance it is half M I1 I2, and this is having its own derivation, but this is from, I think, circuit theories, circuit network analysis, from circuit theory, I think, this derivation. But for now, right now, you should recall, okay, this was the thing. That's all. That's the idea of this exercise. Okay, so for this, the answer will be, so I'll just tell you 10. Okay, okay, you gave the answer for this. Okay, 10, yeah, fine, 10. Okay, 10 is the answer. Yeah, correct. Now, yeah, this is the last question. Which among the following functions satisfy the differential equation? So this is also a quick recall of your maths 1 of your BTech. I think this is being taught in the class also, in the one of the lectures of the first week. So we have d2y by dt square plus b a dy by dt plus c equals to 0. So the solution for this is a e to the power alpha 1t plus b e to the power alpha 2t, and that depends on like the roots, that is b square and 4ac. Okay, and so b square minus 4ac plus minus b 2a, we can get alpha 1 alpha 2. Okay, c is the answer. Yeah, correct, c is the answer. Correct. And c is the answer, and this is a multiple question, multiple correct question, so you can have multiple. So now think more. C is the answer, other answers can be, and I need why for that. Why others can be the answer? First of all, whether others there are other answers or not, just tell me that. Okay, I will tell there are other answers. Now tell me what are the other answers. This is a multiple correct question. C e to the minus t. Minus t, there's no option like that. Okay, D can be okay. D, you are saying D is the answer. C, D. Okay. So why you are saying D as the answer? Just one word you can say in the chat box. So once you get this alpha 1 and alpha 2, that is the root of this equation, then you cannot get e to the power minus 5t. But yeah, you can get this A and B as the answer. Why? Because here, in nowhere in the question, they are talking about the initial condition of this thing or any of the boundary conditions of this. So by boundary condition, we mean we cannot get this A and B values. So if we cannot get these A and B values, then we cannot solve. Okay, so 2 and 3 can be one thing, but just because based on the answers, we know, okay, this is 2 and 3. And yeah, but it can be this also. Maybe this B part is 0 or A part is 0, so we'll get this also. Okay, but this cannot be the answer because we will not get this alpha 1 alpha 2 as 5, any of that as 5. Okay, so like to get to the final value or the solution of an equation, we should also know about its boundary conditions. Okay, so this was for today's live session. So first of all, so any like I would just want to ask you like any any things which I should add from my end so that to make this thing interesting, or like any, or should I go with more revision part, or this format is fine, like solving many questions, or a little bit of revision and then solving some questions. So yeah, you can comment like if this is fine, you can comment this is fine. If you need some changes, you can say I need changes, and you can tell also what are the changes you want. And yeah, yeah, just if you have any suggestions, otherwise if no, then we will continue with this format of like practicing lots like these questions. I'll come up with more good questions for based on the next week lectures, and then we will solve them. And yeah, if nice, thank you, for me this is fine. Okay, so I think if this is fine, we'll go with this. So if in between you get bored or something like that, we can have a 5 minute break in next live session. That will depend. If you will ask for me, they'll give you 5 minute break. But I think this is fine, and then we'll solve more nice questions, so it will help you throughout this course to help you solving these assignments and other stuffs also. Okay, so thank you for being part of this live session. And so I think it's time. So if no other suggestions, then I will end this call. So yeah, you can leave if you don't have any questions or suggestions. If you have any doubts, you can ask me. So next session will be yeah, next session same timings, 6 to 8, and yeah, Tuesday 6 to 8 every week. YouTube link. Yeah, I will. Oh, okay. That I will give you in the discussion forum. I'll have to first upload my this thing this video to YouTube, and then I will give there. So no need to worry. And we'll meet next week this same time, Tuesday. Yeah. Thank you. Thank you. Okay. So I think yeah, I should end this call. Yeah, I'll end this call. Okay. Yeah. Thank you.